Okay, hello students. Today we're looking at our final lesson, I think, in Unit 2, so congratulations on a job well done. We want to look at catalysts today, and so we want to sketch and use energy profile diagrams, including the transitional state and catalyzed and uncatalyzed pathways to represent the changes in enthalpy and activation energy associated with a chemical reaction. We can also explain how catalysts, including enzymes, in particular, affect the rate of certain reactions by providing alternate reaction pathway with a reduced activation energy and hence increasing the proportion of collisions that lead to an energy change. So remember, we've been talking about collision theory, and collision theory requires that the two molecules, for example, colliding together need enough orientation and energy to actually provide a new substance or to create a new product. So what the role of a catalyst will do is it's going to lower the activation energy for a reaction. Now there's going to be no overall change in the enthalpy of the reaction. So if we have a look here, the distance from here to here is not going to change. What's going to change though is the activation energy that you can see here. So the energy required to create a product is going to be lower, and that way we can see that more successful collisions will occur because the energy required is lowered. If we have a look then at the right hand graph, you can see that then if we've got a proportion of collisions that are actually successful, the first diagram shows you, the first part shows you that the uncatalyzed activation energy. So we've got a smaller proportion of products being created, but with a catalyst we've got a greater proportion of successful collisions and therefore a greater proportion of products being made. So there are a couple of different sorts of catalysts. So first of all, we can think about homogeneous catalysts, and they're in just the same physical states of the reactant. So elephant's toothpaste you may have seen, and that's the decomposition of hydrogen peroxide into water and oxygen. If you were to add manganese dioxide, you'd still get the manganese dioxide out, but the reaction would occur so much quicker. Now, a heterogeneous catalyst is in a different state. Now, it's fairly common in industry to put metal plates in the production of ethane, for that would be nickel. In catalytic converters, that's your middle one, so you've got things like vanadium in there to help speed up the process of these hydrocarbons, nitrous oxide and carbon monoxide into other gases there. And finally, in the Haber process, there's an ion catalyst there, and that requires the it changes the amount of temperature needed, so rather than several thousand degrees, it can go to about 800 degrees or 500 degrees Celsius. And so it just makes that production of ammonia so much easier. That's the Haber process. Now, an enzyme is a biological catalyst, I suppose, but they're very specific. They act on specific molecules, and these specific molecules are called substrates. Now, the active site is that actual place within the enzyme that this substrate will act on, which will act on the substrate. And it was proposed back in over 100 years ago now about the lock and key model that enzymes are very specific. So there's a specific key and a specific lock, for example, that works for the each enzyme and each substrate. But the more modern perspective of that is an induced fit model. For example, you'll see that the enzyme will actually change shape when it acts on the substrate. So it's the substrate fits, but it's induced, so it changes the shape. So if we have a look at the decomposition of sucrose into fructose and glucose, you'll produce a water molecule, and what will happen is that you're going to just have this enzyme where the sucrose sits in, and then in this case actually we're going to need a molecule of water to produce that. You will get out our fructose and glucose and be left over with the enzyme. Now you can see that we've got an enzyme substrate complex and an enzyme product complex. So there are these intermediate steps and intermediate energy barriers, and so in this case an enzyme catalyzed reaction or pathway is going to require multiple steps and will have an overall lower activation energy requirement, even though the enthalpy of the whole reaction will not change. So are you able to sketch and use these energy profile diagrams, including the transitional state and catalyzed and uncatalyzed pathways, to represent enthalpy changes and activation energy associated with a chemical reaction? When you are, I'd like you to work on the mastery exercises, please.